the next section. So 11.7, I don't lecture on because it's just a review, but 11.8. 11.8 is, in my opinion, like the gateway to advanced mathematics. It is just a beautiful, beautiful section, and it's not hard. So that's the beauty of it as well. You, after going through all of chapter 11 so far, you just don't want more challenging material. You want it to kind of ease back off a little bit. And I'm not going to say that the rest of chapter 11 is super simple, because that's not true. But at least the idea of the rest of of chapter 11 is not so bad. We only have 4 more sections in chapter 11. And actually, we only have, I think, 11 more sections in the course. That's it. So maybe 10. But all right. So section 11.8 is called Power Series. And these are awesome. Great series. How are Power Series different from all the series you've seen before? They involve a variable. That's just it. So, definition of a power series. A power series centered at A, and we'll talk about that more and more as we move forward, or but often we'll just, by the way, call them power series. So a power series centered at A, or in other words, just a power series, is any series that can be written in the form summation n equals, let's just say 0. It doesn't actually have to start at 0, but let's just pretend. Summation 0 to infinity, so it's an infinite series, of c sub n times x minus a to the nth power. Now, a few things that I need to note here, because this will look terrible to you if you're seeing it for the first time. C sub n, these are just coefficients. They're constants. It's just that you don't know what the constants are, so we call them C0 and C1 and C2 and C3. In fact, if you were to expand a little bit this series, it would be letting n equal 0, C sub 0, x minus a to the 0th power, which is 1, plus C sub 1, x minus a to the 1st, plus C sub 2, x minus a to the 2nd, plus dot, dot, dot. It goes on forever. Okay, we don't know the constants, those coefficients, C0, C1, C2. But they are called the coefficients of the series. In fact, that's what I say right here. C sub n are called the coefficients of the series. A is the center. And if you think about that, why am I calling it a center? Well, think about when you go to graph something, like let's say you want to graph y equals x squared. Well, you know what that looks like. It looks like this. Yay, good old algebra. But what if you want to graph y equals x minus 2 quantity squared? What have you done to the graph? Well, you've shifted it to the right 2 units. You've basically moved its center. And that's literally what you're doing here. You're just moving the center over 2 units. There we go. It's the same picture. It's just moved to the right 2 units. We call that the center. So that's the basic idea of what A plays the role of. It's just the center. What are we considering the center of our series? And that'll make more sense to you as I give you more examples. And this is kind of the focus of a lot of the research that I've done. And so I tend to really love this stuff. So just a fair warning to you. This, to me, is the most important part of calculus. All right. Everything up to this is important too. But to me, this is kind of the cat's meow. This is the good stuff. The bee's knees. Anyway, the values of x for which this power series converges is called the interval of convergence. It's an interval. We will get an interval of x values for which this series will converge, and it'll give us what we call the interval of convergence. The width of that is called the radius of convergence. Again, these definitions are going to be a little bit bulky at first because you just don't know what the heck I'm talking about. But I promise you, as we move forward, you'll start to go, oh, okay. That's easier than I thought it was going to be. It totally is going to be easier. So I just like to squeeze all the information into a single definition. So the largest value of R for which we have an interval of convergence is called the radius of convergence. So let me give you an example of what I mean by that so that it's not going to blow your mind. So for example, if a power series, let's just say it looks like this, summation C sub n x minus 2 to the nth, let's just say, n equals 0 to infinity. I don't know what those constants are. I'm not really concerned about that. But let's say if that power series converges for x in the interval. Now remember, that 2 is called the center. It's called the center for a very specific reason. And you'll see it right here. Let's suppose that that power series converges for x values between, I don't know, 1 and 3. Notice the center of that convergent interval is 2. The middle point between 1 and 3 is 2. That a power series will always converge at its center. This power series will always converge if I let x equal 2, because you're adding up 0 forever. And the sum of 0 is 0. It converges to 0, right? So anyhow, let's suppose that that power series converges not only at 2, but for a interval that's centered at 2. You grow that. This is why being in a classroom is good, because you'd be able to see me do this. You have this interval that's expanding about 2. 2 is the center of your interval. And that is our interval of convergence, which I will not write interval of convergence that much more than this. I usually use IOC for interval of convergence. Not just me, everybody uses IOC for interval of convergence. And the radius of convergence is 1. Why? Because on a number line, here's my center at 2, and I'm telling you, fictitiously, but I'm telling you that that series, power series right there, I'm pretending as though it converges for all of these highlighted x values from 1 all the way up to, but not including 3. And the radius of that is a radius of 1. That's the radius of convergence. Now it should be like, oh, that's all it was? Okay, that's a lot of heavy language up above just to say what you just said. Well, yeah, but you have to kind of show an example to make it make sense. That's the only thing. So a couple notes here. One, a power series is just a polynomial function, an infinitely long polynomial function. If you look at this power series, expanding it out, it's just a very long polynomial. X minus a to the first, x minus a to the second, we'll have an x minus a cubed, x minus a to the fourth, and so on and so forth. It's a big old polynomial. All power series are just polynomials. Welcome to real mathematics. That everything you learned in the past, I learned the secant, I learned the sine, the tangent, the cosine, I learned the arc tangent, I learned the natural log, I learned 1 over the square root of 1 minus x squared, whatever it is. They all can be represented by infinitely long polynomials. All of mathematics boils down to polynomials. That is awesome, because if I want to integrate or differentiate, I'd rather integrate or differentiate a polynomial rather than an ugly function. And that's also, by the way, why I say f of x is equal to that, because a power series is a function of x. That's a very impactful statement. So I want to make sure that you guys are following along. This is the first example of a series that contains variables. Although technically we had a homework problem with one earlier. So, all right. I don't think there's anything else on my lecture notes here. So let's go ahead and hop forward. So let's expand the following series And I say use Wolfram Alpha. I'm going to use Desmos to visualize this. So expand the following series and state the radius and interval of convergence. Okay. How the heck do you do that? Well, expanding the series shouldn't be a mind-blowing thing. Let's go ahead and just showcase what I mean by expanding the series. This is definitely a power series, even though it may not look like the definition. It is. The coefficients are 1 over n factorial, and it is x minus 0 to the nth power. It totally is a power series. These right here are the c sub n's, and this is x minus a to the nth. Notice the center is at 0. Incredibly important to mention. The center here is at 0. We are expanding this polynomial. That's a way we're going to say it. This is a polynomial expanded about x equals 0. I'm telling you, it's one of my favorite topics. Okay. So let's go ahead and see what this expands out to be. I'm going to just rewrite it in the form that you see up above because I dislike writing it as 1 over n factorial times x minus 0 to the nth. I just think that's a silly way to write it. So let's go ahead and expand this polynomial out. When n is 0, we get x to the 0th over 0 factorial. When n is equal to 1, we get x to the first over 1 factorial. When n is equal to 2, we get x to the second over 2 factorial, and so on and so forth down the line. You go forever. You don't want to, right? Just to remind you, 0 factorial is defined to be 1. So this is going to be 1 over 1 plus x over 1 plus x squared, over 2 factorial, and then plus x cubed over 3 factorial, plus ... down the line. That's our infinitely long polynomial. Goes on forever and ever. That is not mind-blowing. It's just us kind of expanding it out. Nothing big. But how the heck do you find the interval of convergence and the radius of convergence? Generally speaking, you actually find the interval of convergence first and then state the radius of convergence. Actually, no. You find the radius of convergence and then state the interval of convergence. So let's go ahead and ask ourselves, how do we find radius of convergence and interval of convergence? How is that done? Well, it comes down to asking the question, when will this converge? And that is engaging all of sections 11.2 through 11.6. You have to test this series for convergence. We need to find when the series converges. And so we're going to use a test. The easiest test, now look at this. If you're looking at tests to use to determine when this converges, or quote unquote, if this converges, you're going to start throwing out tests immediately. For example, I'm not going to use the integral test because it has a factorial. So factorial implies no integral test. Just not going to do the integral test. It's a terrible test to use if you have a factorial. In fact, it's impossible to use if you have a factorial. Let's see, the other test, well, there's a divergence test, but I don't want to prove divergence. I want to find out when it converges. So forget about divergence test. It's not a geometric series. And to be honest with you, the comparison tests are going to be pretty terrible here as well because there's a variable in that numerator. Well, there's a reason why I love the ratio and root test. And here's why. Because when you're doing power series, you're pretty much only using ratio and root tests. Sometimes you have to use alternating series tests, but let's go ahead and use the ratio test here. I'll zoom out. ratio test. We'll take the limit as n runs off to infinity of the ratio of the n plus first term. Actually, I'll write it this way. Of the n plus first term times the reciprocal of the nth term of our sequence. Now, looking at our sequence that our series is based upon, it's an x to the nth over n factorial. So let's look at the n plus first version of that. It's x to the n plus first over the quantity n plus 1, n quantity factorial. And we're going to multiply that by the reciprocal of the original sequence. So what's wonderful about power series is that it happens right after you've learned the ratio and root tests, and all it uses is the ratio and root tests over and over. So you get multiple practice problems. It's a really, really great section. So the reciprocal of the original series or sequence is n factorial over x to the nth. Now, these absolute values are going to be critical to leave on there because we don't know if x is positive or negative. But things do clean up a little bit. For example, this becomes the limit as n runs off to infinity of the absolute value. I see x to the n plus 1 upstairs and x to the n downstairs, so that'll leave us with the power of x upstairs only. And n plus 1 factorial is n plus 1 times n factorial. So you can see the n factorials will cancel beautifully. And here's the trick, not trick, but here's the mathematics behind the scenes. X does not rely upon n. I don't see an n attached to that x as a power or anything like that. So I can move that absolute value of x outside of the limit. I hope everybody's okay with where we have arrived. Now, as n goes to infinity, that limit of 1 over n plus 1 tends to 0. And 0 times anything that x is, doesn't matter what x is, because x is just some number. Somebody's going to hand us a constant eventually, and they'll say x is 5 or 2 or pi or negative pi or e or something like that. Doesn't matter, because 0 times it will always be 0. So this limit right here is going to run off to 0. 0 times that x will always turn into 0. And by the way, isn't that less than 1? Therefore, no matter what x is, let me actually write this down. Thus, no matter what x is, the limit is less than 1. And so the power series will be absolutely convergent by ratio test. So the question was, find the radius and interval of convergence. And we find that it will converge for every single x value in the universe. That is, it'll converge for all real numbers. So the series, power series technically, is convergent on negative infinity to infinity. Notice the center of that interval is 0, which is where our power series was centered. Let me just zoom in over here. Our power series was centered at 0. So that's our interval of convergence. The radius of convergence, it has an infinite radius. All right. Now, before I showcase what we've just done visually, I want to take questions. So if you do have questions, please ask. Not all, by the way, not all power series have an infinite radius of convergence. Okay. There will be some that restrict down, but this is a very famous power series. So it's kind of nice to start with this one just to showcase it. How is the interval of convergence all real numbers? No, actually, I'll tell you how it's all real numbers when I give you the visual. It's all real numbers because no matter what I plug in for X, remember we did the ratio test, right? And the ratio test is going to show us that this series will converge if the ratio test is less than 1, if the limit is less than 1. And we took the ratio, cleaned things up, got to this point, and this limit tends to 0 times absolute value of X, which is still 0. And that's always less than 1. No matter what X is, that limit will end up being absolute value of X times 0 or 0, which is always less than 1. So again, no matter what X is, by the ratio test, we have convergence. So it'll converge for all values of X. If you let X equal 27, well, if that's 27, 27 times 0 is still 0. So the ratio test still shows that the limit is less than 1. If you put in 27 million, right, still 27 million times 0 is 0. And so that limit's still less than 1. So you still have convergence. So it doesn't matter what your X value is. Yeah. Now I'm going to show you probably one of the most impactful pieces. Let me just load this up. Desmos, except you need a dot there, Desmos. Okay, so let's go ahead. I'm going to share my screen. This is like exciting to me. I love this stuff. So here we go. Here's my screen. And I'm going to just go to the graphing calculator because that's important to me. And what we were looking at was the sum, S-U-M, from n equals 0 to, actually, I'm going to call this f of x too. F of x is equal to the sum n equals 0 to, let's just add up the first term, okay, of, it was x to the nth. Let's see if it does factorials. Hopefully it does, because it'll be a bummer if it doesn't. Over n factorial. Okay, good. So when n is equal to 1, think about that. If n is equal to 1, what you're really looking at is y is equal to, well, when n is 0, you get 1, plus when n is 1, you get x to the first over 1 factorial, which is what we just are looking at. I'm going to mute this for a moment. Let's see if we sum up the first two terms. Again, that would be 1 plus x squared over 2 factorial. Which, by the way, for some reason, oh, there we go, which is that parabola. All right. What if we sum up the first, oh, I don't know. Let's sum up the first 20 terms. What if we sum first? I could break Desmos very easily, so let's not go past 100. So let's sum up the first 60 terms. Let me zoom out. What does that function look like to you? And I'm going to somehow, where's my chat? Where's my chat at? There we go. What does that function look like to you guys? Yeah, it looks like an exponential. Let me mute this out. Let me delete this. And let me type in y equals e to the x. Here's y equals e to the x. Let me move. Let me turn off the grid because it's annoying me. There's y equals e to the x. You go back here. I'm going to put this back at 2. Okay, be ready. Something cool is going to happen, okay? I need everybody on board paying close attention. And if you want reverse contrast, there you go. You got it. Some people prefer reverse contrast. I thought there was a way that I could do projector mode, but they must have taken that off. Oh, there we go. Okay. So I have this power series. It's a function of x. It's a big, long polynomial. If I only have a couple terms in it, a zeroth and a first term, it looks like that. Remember, this power series is actually, oops, centered at 0, right? That's what it technically is. 2 terms, 3 terms, 4 terms, 5 terms, 6 terms, 7 terms, 8 terms, 9 terms, 10 terms, 10 terms, 11 terms, 12 terms. And when I say 12, technically it's 13 because there is a 0th term in there. 13, 14, 15, 16, 17, 18, 19. Do you see that each time I add a term to the series, it gets closer and closer to e to the x? Let me turn off e to the x. Let me turn on e to the x. You had better believe that's freaking awesome. And notice it's centered at 0. Again, let me just showcase the polynomial that we're building. That's the blue curve right there. That's the polynomial we're building. Here's e to the x. So e to the x right now is being modeled by this 19th degree polynomial. And it's being modeled excellently, at least from around, what is this, -7, maybe, yeah, let's say from -7 to roughly probably positive 50 or something like that. It's a pretty good approximation. That radius of excellent approximation, which we'll call a radius of convergence, will grow as we add more terms. So if I add more terms, go to 60 terms, while it doesn't look like it's better, it actually is better. It's just that Desmos can't handle the computation. There we go. It finally caught up to me. Let me turn this off. Yeah, so I just broke Desmos. You can see nothing's happening because Desmos can't keep up with the computation. There it goes. So you can see the blue curve right there. That's the first, technically, it's a 60th degree polynomial approximation to e to the x. You had better believe that's pretty awesome. This polynomial is a wonderfully great polynomial to approximate e to the x near to 0. So you don't even need 60 terms of this added out, or the 60th power added out. You could just go to the second power. Notice I'm looking at the sum from 0 to 2 of x to the nth over n factorial. It's just a second degree polynomial. It's just a parabola. But I can now approximate, for example, let's approximate e to the 0.5. We happen to know that e to the 0.5 is 1.6487 and some change. What about my polynomial approximation, f, evaluated at 0.5? That's not too bad for not having if I didn't have a calculator and all I had was a polynomial and plug in a half to a second degree polynomial, that's not a bad approximation. And the closer I get to 0, the better the approximation is. So if I want to know what e of 0.25 is, I can just plug in a 0.25. That's a much better approximation because I'm closer to the center of my power series. The closer to the center, the better you are. Unless, for example, you want to add up more than just the first, or unless you want to get more than a second degree polynomial approximation. If you want a 20th degree polynomial approximation, look how nice our approximations are now. They're exact all the way out to 9 digits. And if I want to know what e to the 0.5 is now, it's still exact out to 9 digits. If I want to know what e to the first is, which we know is 2.71828 and change, I'm still exact out to that many digits. If I want to know what e to the 10th is, well, that might be a little bit tough, but let's try it out. Now I have some error. That's because I'm 10 units away. So that's a significant distance away. These are power series. This is where it's at. Every function, pretty much, the vast majority of them that you've played with in mathematics can be represented by a power series. Let me bring up my laptop. There we go. So this is, in my humble opinion about mathematics, this is one of the most important topics in mathematics. Being able to transform a given function that's terrible into a power series. All right. Now, do you have to do that? Like go to Desmos? No, you don't have to go to Desmos, but man, the visual's worth a million, right? It really does showcase the beauty of what we're doing right now, which is building a polynomial approximation to a possibly terrible function. And by the way, we didn't prove it, but this is this power series right here, if you expand it out forever, is actually e to the x. That is the polynomial representation of e to the x. And we will have other ones for sine of x, cosine of x, natural log, tangent, arctangent, all of them. You don't have to memorize them, although e to the x, you should memorize that one. But anyway. All right. So note, obviously, I hope it's somewhat obvious. Let me go ahead and write down the power series down here. C sub n x minus a to the nth power to infinity. All right. So the first statement here is, obviously, if x equals a, the power series is exactly 0. If you let x equal the center, for example, in that e to the x situation, we centered it at 0. So if you were to plug 0 into our previous example, into this guy right here, you would get 1 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. Obviously, that converges, right? It converges to 1. So that is the point of that sentence up here. If you if x equals a, then the power series is not exactly 0. It's actually exactly c sub 0. So just plug it in. If you let x equal 0, you get the summation n equals 0 to infinity of c sub 0 times 0 and or c sub n, sorry, times 0. Technically, you have to expand out the first term. So I'm going to expand out the first term. I'm going to say this is c naught plus the summation n equals 1. So I just spit out the 0th term of the series so that I don't have to have this conversation about what is 0 to the 0th power. So cn x minus or a minus a to the nth power. Now think about 0 to the first, 0 to the second, 0 to the third, 0 to the fourth. There we go. So if you plug in the center of the series, you will find that it's convergent. So all power series converge at the center. And in fact, let me highlight this right here. That's what this is saying. No matter what, we are guaranteed that our power series will always converge at the center. Okay. So let's see. Thus, we want to find the largest interval about a. I'm just reading this right here. Where our power series still converges. That is, we want to find a radius so that the power series converges from the center minus r to the center plus r. You have some center. You just want to find this interval of convergence, a minus r to a plus r. We want to find out what that interval of convergence is. The series may also converge at the endpoints, but this must be tested separately. And we'll get into that later on. The reality is that you can have it converge, let's say, at the left endpoint, but it won't converge at the right endpoint. So you get these half open intervals of convergence. We'll deal with that as we move forward. Don't really worry about it. But this last piece of advice is important. If the original series is geometric, well, we know from the geometric series, they don't converge at the edges. In other words, geometric series converge if the absolute value of the common ratio is less than 1. Notice it's not less than or equal to, but less than 1. So because of that, the interval of convergence will never include the endpoints. And we'll see that in a lot of examples. So don't worry. All of this will sound foreign and start gluing together as we move forward. Okay. All right. So that's just a little page of advice. That main thing to take away from this is that if it's geometric, you don't have to test the endpoints. And if not if, and all power series converge at their center at the bare minimum. They all converge minimally at their center. They might converge elsewhere, but they definitely converge at their center. So let's go ahead and play with some power series. Let's just do a ton of examples because it's good to get the experience, right? So here's a power series because it has an x in it. It's a function of x. And I want to find out what the radius and interval convergence are. Well, note, if you take a look at this power series, it could be written as follows. Now that's pretty rad. I'm pretty happy with that because while it's technically not a geometric series because this n is not a constant nor is x, I can at least say that we require that x minus 2 over n be less than 1, right? So that's, it's not really going to be helpful here. So maybe I should just do the root test so that we can move forward with this. So let's go ahead and do the root test rather than confuse you with that. So I'm going to do the root test and take the limit as n tends to infinity of the nth root of the absolute value of that sequence. The sequence is the nth power of x minus a, or x minus 2 over n. Oh, and I should also mention here that this series is centered at 2. Basically, you could ask, the easiest way to find the center for a series is to say, what would cause that to turn into 0? 2. 2 would cause that to turn into 0. So there you go. All right. So let's go ahead and take the nth root of that nth power. So we get the limit as n goes to infinity of the absolute value of x minus 2 over n. Remember, n is positive, so it doesn't actually need the absolute value on it. The x minus 2, on the other hand, we don't know if that's positive or negative, but we can move the absolute value of x minus 2 off of the limit itself to get this right here. I just removed the absolute value off the n because, well, n is positive. There's no need for it. The absolute value of x plus 2 I moved out front because it's not to the nth power anymore. So it's, as far as a limit is concerned, it's constant to the limit's concerned. Okay. As n goes to infinity, again, we end up with this highlighted piece tending to 0. Think of any number you want to plug in for x. Doesn't matter what the number is. When you multiply that value, x minus 2 absolute value, by 0, it's always going to be 0. Always. And that, my friends, is less than 1. And remember, the root test tells us that we have convergence, absolute convergence, in fact, if that limit that we started with, this guy right here, becomes less than 1. Since the limit is less than 1 always, this series, the power series, is always convergent for any value of x. So thus, the interval of convergence is again negative infinity to infinity, and therefore the radius of convergence is infinite. And if you want to see this, I highly recommend just using Desmos. This is the first time in a long time where a technology has come out where you can actually help. It helps visualize Calc 2 concepts. So you could use Desmos liberally here just to help you visualize what's happening. I don't know if Desmos would be able to handle large polynomial computations of this, to be honest with you. But I'm willing to risk it. So I'm going to do it. Let me share my screen, which I thought I did, but for some reason it didn't. Okay, there we go. And I'm going to turn off all this stuff. And I'm just going to change this to 2 because I don't know if Desmos can handle a computation. And it was x minus 2 to the nth. So let me change that to a 2. Notice the center moved when I did that. And it was over n to the nth. Okay, n to the nth. Yeah, that's right. So let me zoom out. I'll start with n equals 0 to 0. It'll be a flat line. But then I'll go to 1, and then to 2, then to 3, then to 4, then to 5. So what you're seeing is increasing polynomial powers that give us what our power series is going to look like in the long run. I'm just curious what it is. It's hard to tell what power series are, actually. They can handle all these, so that's good. 20, 21, 22, 23. Okay, so it looks to me like almost exponential, right? It's got this dip down, it climbs up. So this 23rd degree polynomial is probably a pretty decent one to approximate whatever function this power series represents. It's accurate, 100% accurate at x equals 2 at the center. However, it starts to lose accuracy as you move away from x equals 2. Now, again, I'm not 100% sure what this function actually is. Power series, you generally can't tell what their original functions are if somebody just hands you a power series. But such is life. All right. Now, before we leave for the day, and remember, I don't have office hours today because I'm picking my wife up from the airport. However, I want to do one example where the radius of convergence is non-infinite. So I'm hoping that that's this one. I don't know if it is because I can't tell by just looking at a power series. Nobody can. So here's a power series. Let's go ahead and do the same exact stuff we were just doing. Let's determine the interval of convergence and radius of convergence for this power series. Again, I'm going to just, in this case, not use the root test because this is not all to the nth power. Instead, I'll do the ratio test. Notice it's just one of those 2 tests. I don't really do any other tests when it comes to power series. That's the beautiful thing about power series. It's much easier to work with. So let's see, this limit as n goes to infinity. Remember, we want to see for what x values is this going to converge. Well, let's find out. We have the absolute value of the n plus first term. Times the nth term. Reciprocal of the nth term. Now, this one is interesting. When you clean this up, this will be the limit as n tends to infinity, absolute value. Notice as far as x minus 2's go, we have a single power in the numerator now. Let me go ahead and write that down because the nth powers of them canceled. And then we have this product of n squared plus 1 over, and I'll distribute this out, n squared plus 2n plus 1 plus 1. Now remember that x minus 2, that does not rely upon n, so I can move that outside of the limit. I have the absolute value of x minus 2 sitting outside the limit. And here is the first example of the rest of your life. The first example of how you're going to do the rest of these problems. So we get to this point right here, and notice that limit does not tend to 0. What does that limit tend to? 1. Okay, great. Thank you. So this is going to be the absolute value of x minus 2 times 1, or in other words, the absolute value of x minus 2. If I want that power series to converge, what do I want the ratio test for that limit to be? What do I want that limit to be? Less than, thank you very much. Alyssa, you're right. You want it to be less than 1. For convergence, so to converge, we require the limit to be less than 1. That is, we want the limit, which is the absolute value of x minus 2 times 1, to be less than 1. And here we go. This is how they're all done, unless they're infinite radius of convergence. But the rest of them are going to work like this. If you think of a number line, we're centering at 2. My radius, look at that. The radius is right there. It's telling us I want to center at 2. That's what this x minus 2 is saying. I want x values to be centered at 2, and I'm allowing for a wiggle of size 1. Ta-da! So our interval of convergence is from 1 to 3. And the radius of convergence is 1. That's what the radius here is. So that is a really, really cool problem. Now, the one thing I do need to mention here is that because that series was not a geometric series, I have to test the endpoints. So I'm going to point an arrow at this, and I'm going to say we must. It's incredibly important. We must test endpoints. But we're at the end of the day. We will do this next time. We will start here next time. All right. So I hope that you got kind of excited about power series. I think they're really, really cool. And I love the idea that you are given a function, and that you can represent that function using a polynomial. And I'm going to leave you with one very beautiful function here. I'm going to go over here, zoom out a little bit. I don't have to actually zoom out too much now that I think about it. And I'm going to create a little power series, and I'll let you think about what that power series might be. It'll be a -1 to the nth. I'll say it's an x raised to the, somebody tell me if you want odd or even. I'll take the first one. Whoever says odd or even. Odd. Okay. So I'll say x to the 2n plus 1. I need to put the plus in the numerator or in the exponent. So we'll put the plus here, plus 1. And I'll divide it by 2n plus 1 factorial. And hold on, before I do that, I'm going to back this off to be 2n plus 1, and I'll put a little factorial in this. All right, so you see this. Now, if I start to increase this, 3, 4, 5, 6, 7, 8, 9, 10, oops, 10. I undo 10. Put 10 in here. What does this function look like to you? Looks like the sine curve. You are absolutely correct. And the question I asked you, let me turn off this. There's the sine curve. There's the power series. The question I asked you, odd or even, tell me the sine curve, odd or even function? Okay. Tell me the cosine curve, odd or even function? even. So if I turn on the cosine and I decided to make these even powers, there's the power series. And you can keep going, right? 11, 12, 13, so on and so forth. Pretty beautiful stuff. I got to tell you, this is awesome. So there's a polynomial, the infinitely long polynomial version of the cosine. So it makes computations, trust me, a lot. This is actually how Desmos computes. If you want, or any type of algebra system, computer algebra system, if you go to a calculator and type in integrate, or you go to Photomath, whatever it is, and you say integrate cosine of x from wherever to whatever, it's actually doing a polynomial. It's not doing, it doesn't have things memorized. It has a polynomial expansion. It actually builds the polynomial expansion on the spot. All right. Okay. I am done amazing, at least myself, because I find this stuff to be pretty awesome. And so I will see you guys on Friday, and we'll continue through this. No quiz today, by the way, right? No quiz at all. So you guys have a wonderful day, and I will talk to you later. Take care. Bye-bye.